Welcome back. Today, topic 6, power transmission elements 2. We're going to do screws and gears. Let's jump right in. Lots of different applications, screws and gears. We got lots of new toys here added to the design deck. Jump in. Screws. Where do screws come from? How old are they? Was it Archimedes first describing a screw to lift water? Where did he come up with the idea? No one really knows. But they're amazingly useful, found all over the place. Thinking of a corkscrew, which actually threads itself into the cork on a bottle, driven by what looks like a screw but actually is not. This is a circular rack for a rack and pinion. And why is it round? Why does it look like a screw but it's actually not? Why is that? That's a very nice mechanism to do. To the thread on a bolt and its mating nut. Apple peelers, a dirt screw, all over the place. A roller screw, recirculating roller screw, to a ball screw, which uses recirculating balls. Why do they use recirculating elements in these devices? We'll get to all of that. One of the most useful and powerful machine elements around. Lead screws and ball screws, what is the difference? So all ball screws are lead screws, but not all lead screws are ball screws. Generically, the term lead screw refers to a screw with sliding contact friction between the threads of the nut and the screw. Why would you put little balls in here to recirculate as the nut moves? So you have rolling contact friction and much higher efficiency. And when you do the analysis of the screw, remember from our earlier lectures, you have work in equals some efficiency times work out. Oh, excuse me. Efficiency times work in equals the work out. Conservation of energy. The work in for a screw, you apply a torque. You're twisting it through one full rotation or 2 pi radians. So the efficiency times the torque in times 2 pi. And whenever you're working in energy, you have to use radians. You don't use degrees for angular motion. Equals the torque out times what? This is for a screw. This is a screw. So for example, I'm applying the work into the screw itself, and then the work out I want to get from the nut, the motion of the nut. But what am I talking about torque out? That's not the motion I want. What I want is the linear distance this is a force. This is torque. This is radians, or angular motion. How do I know what is happening here? So when you're solving these kind of problems, you want to think of 2 things. Remember that the units match, that the input units, for example, torque is the units of force acting over meters. And radians as an angular measure is actually unitless, has to equal, and the force is the units of newtons. So that means this is times something of units with meters. The next thing you look at is geometric compatibility. A screw contains the nut, or the screw system contains the nut and the screw constrains the nut to move as prescribed by the interface between the threads of the nut and the screw. So when I take this screw holding the nut and I rotate it that's 1/2 rotation and 1 more full rotation, the screw will advance by what is called the lead. The lead is how much this helix advances in 1 rotation of the screw. So that tells me that this is the lead of the screw, my efficiency. And what is of interest to me is, if I put this much torque into this screw, how much force can I get out of the nut? So the force, I'm sorry, up here it says linear distance. This should be linear distance is the lead, and the force is the unit. The force out equals the torque in times 2 pi over the lead times the efficiency. Right? What does this tell you as a machine? Wow, if I make this small, I can get a huge force out. Let's test that hypothesis. If we go here to this clamp that's holding this device, which we'll get to later when we talk about screws, I can put just, so it's just barely here, and you see how this is wiggly, and just by putting just a little bit of torque on it, see, I'm just a little bit, wow, that's really holding on there tight. I could have done the demonstration where I take the clamp and put it on my finger and apply a little bit of force, and you'd hear the bone shattering, but that would not be a good thing. Okay? So this is the wonderful power of the screw. You get a huge output force if you have a fine lead. And okay, efficiency, good efficiency. This is where the limits become apparent in real systems. If you want to apply a torque to a bolt and have a huge force in the nut, that means you want to have a low coefficient of friction between the threads, which means the threads have to be lubricated. If you just take a cruddy old thread with a rusty old nut, you're not going to generate that much force. Lubricate it, and oh, that works really good. Same thing with a ball screw or a roller screw. If you have rolling elements in here, the efficiency of this screw will be a function of, yes, the apparent coefficient of friction and the actual lead of the screw. Ball screws and roller screws can be 90, 95% and better efficiency. So this can be 90% easily for a rolling element screw. On the other hand, if you have a sliding contact thread screw, this may be 50% for really good low friction material, Teflon-based lubricants. It can be down in the 30% range for steel nut on steel screw with basically no lubrication. Where do you see screws in machines? Here's a screw shaft for a lathe. Here's a cross-section through a machine design where you see linear bearing carriages. That would be these type of carriages. Driven, for example, if you had table on top, attach the nut to the table such that when you rotate the screw shaft and the nut doesn't rotate, the linear bearings with the carriage table would move. There's a lot of detail that goes into this, and let's examine this picture here. First of all, the screw shaft mounted on the ends with bearings. Very subtle differences here in the way this bearing is mounted and this bearing is mounted. This bearing is mounted constraining the shaft to take thrust back and forth. And the way these bearings are mounted, it actually gives some stiffness to the screw shaft this way. Flexible coupling to the motor, because the motor shaft is very hard to get exactly aligned with the screw shaft. The other end of the system, the lead screw or a ball screw shaft, goes through the bearing, and it's a sliding fit with the ball bearing unit here. So all the thrust of the screw that happens when you turn the screw and the nut is not allowed to turn, so the nut wants to move, and if something's restraining it, that's a force that then is transmitted through the screw to the bearings here, or taken up at this one end. Why is it mounted this way? Well, if this is a high-speed motion that goes back and forth, which a lot of machines are these days, you generate heat. The heat comes from the efficiency is finite. That heat is generated at the thread interface, and all the heat goes into the nut and the screw may end up being tens of degrees hotter than the rest of the machine, and it'll expand. And if you had this nut on the end here fully constraining the screw, the shaft could expand and then buckle. Let's come back to reciprocity, risks, countermeasures, following through the whole Fred Park design thinking. How would you stop that? How would you mount the screw in bearings that hold it at both ends such that the screw got hot and expanded, it wouldn't buckle? Why would you want to hold the screw mounted at both ends so this pair of bearings and this pair of bearings, both sets can take forces in either direction? What is the stiffness of the screw shaft? If I just said I want to make this a very high-speed system, why do I want to make the screw shaft as small diameter as possible? Why not to get a really stiff machine tool carriage that can just cut really heavy loads? Don't I make this shaft big and strong? Why do I want to have a small diameter? Let's go back to a little bit of thinking. When you're designing a machine, there is the philosophy to understand. There's the awareness of your machine elements as what's available. And there's also, remember in our function requirements, design parameters, analysis, right? References, risks, and countermeasures. Watch what happens here. If I make as a functional requirement, I need a very high stiffness actuator. Design parameter for that would be, in other words, what way you can achieve that would be, say, a ball screw. I also need a very high speed actuator, linear actuator. Ball screw, or maybe a roller screw. We can decide later, but basically we're going to use a rolling element system. You could use a lead screw here, but when I go to high speed, that kind of nixes the lead screw in general. You're much better off with a ball screw because of very much more higher efficiency. And you merrily go happily designing along. Whee! Well, on the details on the next level of the Fred Park sheet so this is on your strategy. When you get to the concept and the mounting, you say, wow, let's look at the analysis here for the stiffness. And the stiffness is, how do I do the stiffness? Remember the structural loop. Okay? The concept of the structural loop. Here, and it goes through the bed. Now where? Somewhere this carriage, there's going to be a part on the carriage, and here's your tool, for example, that's attached to a spindle head on the rest of the machine that comes around mounted to the bed of the machine. This structural loop will go from the nut, table, all the way through the rest of the machine, through the head, through the tool, bing, back to the beginning. This is a big, powerful spindle, big, powerful axes. Notice the axis in compression here, so you're not, when you're pushing this way, you're not compressing the screw. You're, a lot of this cast iron. Tool might be bending, but let's make this a real heavy, thick carbide shaft. So you're worried about screw shaft stiffness. Oh, how can I make it better as a structural loop? Huh. What is the total stiffness of the machine? Counting your elements in the loop, there's a stiffness of the screw, stiffness of the nut, the stiffness of the mount, the stiffness of the bed, stiffness of the rest of the machine, such that the system stiffness equals 1 over K screw plus 1 over K nut plus 1 over K mount plus 1 over K rest of machine. So the secret to making this higher, let's assume that this is really big. So this is huge. So this term here goes to 0. The stiffness of the mount, I'm not sure. Stiffness of the nut, I don't know. These are probably all on the order of each other. If I look at this, I say, what options do I have? Well, I can up the size of these two, or I can make 2 of these. I could add another path through the structural loop. So this could be up to 2 times. So now I go back and I say, wow, okay, what are my options here? Well, I can use things like a double nut to get higher stiffness. But the only option, so this might be 2 times the nut. But my only option for the screw itself is to go the diameter larger. And watch what happens. So now, remember, this is all in the analysis column. And this is on the early concepting of my machine that I'm doing this type of analysis. So I want to know how the screw shaft stiffness goes with the diameter. I also want to keep in mind my other primary function or requirement of the speed that I want to go. So let's look at this one here. The stiffness of a shaft in compression or tension. What is stiffness? See, if you don't know exactly and you can't rattle off A over L, think it through. What do you want to accomplish? Stiffness is newtons of force. I push on and I get some displacement, newtons per meter. And what makes sense? It makes sense that if the modulus of elasticity of the material is involved, it has to be, because if the stiffness of a rubber screw is going to be a lot less than that of a steel screw, so the modulus of elasticity. And the bigger the cross-sectional area is, the stiffer it should be. But the longer the shaft of the screw is, the more of a spring it is, divided by L. Let's check our units. The units of the modulus of elasticity, newtons per meter squared. The units of area are meters squared, and the units of L, length, are meters. So I get newtons per meter. Check. Fine, what's that got to do with D? Well, the only thing that varies with the diameter D is the area. So the stiffness goes like the diameter squared, pi over 4. But this is the driving relationship for this property of the machine as governed by this machine element. And this is what's very important when you're designing your machine, that you start looking for these driving relationships, these dominant factors. Now let's continue with the next functional requirement, which is the speed. What's the speed driven by here? What are the dominant parameters here? Well, I want to be able to move this thing as fast as possible with as little effort of the motor going into just accelerating the screw shaft itself. I really want all the whoop, oomph of the motor to go into moving just the parts. So ideally, the rest of the machine doesn't have any effect. And if I want to accelerate all of a sudden, we have this good old Newton's law, F equals ma. Or for a screw rotating, I want to move it real fast. The torque equals the moment of inertia times the angular acceleration. This moment of inertia, or sometimes it's written as IP, right, the polar moment of inertia, because I'm doing rotation of a screw shaft, goes by what? Well, you can work your units here again. This is Newton meters. This has radians per second. And a Newton is kilogram meter per second squared. You'll find that what is the polar moment of inertia? Anybody want to guess? It goes like the meters to the 4th power. Okay? So, and what else is missing here? Density. This is because you have to get your kilograms in somewhere. But the critical parameter is meters to the 4th power, which means that the torque required of the motor to spin the screw shaft goes somehow by meters to the 4th power. What about the length of the screw? How does that enter into this? Does this go like now the torque to move the diameter of the screw to the 4th power? You guys can look this up because you've all had beginning physics. The answer is yes, it does. And now the challenge you have is that if I make the screw shaft bigger by a factor of, let's say, I want to increase the stiffness by a factor of 2, so I make this 1.4 times bigger, so 1.4 squared is 2, the rotary inertia will go up by a factor of 4. So by making the screw shaft bigger in diameter just so I can get higher stiffness by a factor of 2, it takes me 4 times the torque to accelerate the load. Ouch. It's not a wise design decision for a high-speed machine where you want to get the stiffness up just to increase the diameter of the screw shaft. You're better off doing things like longer nut or figuring out how I'm going to be able to make this bearing here anchored to the screw and accommodate the fact when it gets hot, the screw wants to grow and then buckle. So let's look at that design problem. How would you handle that? And you see what we're doing here as we're continuing on with the lectures. Earlier on, we were doing on the broader philosophical basis, starting to introduce some more and more design detail, as you saw in topic 4. And here, for example, with screws, we're really diving in deep. The process is what's important here. The details of the analysis you can read a lot in the text and a lot of reference books on things. But what's important is you understand in the early concept phase how you look at your machine, how you think about the structural loop, how you identify the dominant geometric parameters, particularly in your machine elements that are often highly stressed. Identify these relationships, and knowing these powers and the sensitivities to small changes in dimensions, for example, it gives you a powerful license to go after the low-hanging rabbit. So let's continue with our Fred Park sheet up here. So we're going to pick a ball screw, and here we're going to pick a ball screw. Highest stiffness, by the way, you can get with a roller screw nut. Roller screw nut give you much higher stiffness in the same package than a ball screw nut. A little more expensive, harder to get element, but if you really, really pushed for it, you can use a roller screw. And we did our analysis, so we check, and this told us use as small shaft as possible and double mount the shaft. So we have mount, both ends. shaft support for thrust. Wonderful. We also happen to know that this is done quite often in machines. But the risk is, for high speed, it gets hot, shaft expands, and can buckle. Because if this is the shaft, and it's supported by the bearing, so it thinks it's built into the wall, if this gets longer, the walls ain't moving, it's going to go boop and buckle. What's our countermeasure? No buckle. What's the opposite of expands and it's under buckling is a compression mode? The screw is essentially being compressed by it wanting to expand, and then it buckles. No buckle. So what's the mechanism of buckling? It's essentially compression. I don't want it to buckle. What's 1 over compression? That leads to tension. Tension. So if I know that the change in length of the screw shaft is going to go from here to, say, here, why can't I initially mount the screw shaft in bearings and pull it, and in other words, pre-tension it or preload it? So the screw is mounted, and I won't pull so hard to break this because I've only got one of these. But if I pull on it, you can see it's probably stretched by 2 or 3 millimeters now. Actually, not that much. And when the screw turns now, I will slowly replace this tensile strain of preload with the thermal expansion. And as long as my thermal expansion is less than how much I pre-tensioned it, the screw will always be in tension a little bit and it will not buckle. And if these are high quality rolling element bearings, the amount of drag I will get from the force placed on those bearings is low. I can even go so far to remember that there are special types of bearings called ball screw support bearings that have very special angles between the balls and the races, such that they take very high thrust loads very, very efficiently. So you see how we've gone this full circle, starting way back in topic 1, all the way through how we apply these thinkings from the fundamental principles, all the way through if you have a screw shaft, this machine element, how do you use it? Think about it in the context of a machine and the types of analysis you're going to need to do to move forward. So let those thoughts simmer here for a minute while we start thinking in even more detail about the forces that you have to deal with. When you start looking at the screw thread itself and the types of angles and what the forces look like, you can actually calculate, given just the coefficient of friction between materials, the screw efficiency. That calculation is well known how to do that. And even more, it follows that you can calculate, is the screw back drivable or not? So a back drivable screw is one where in its own weight in a high efficiency mechanism, it just drives. A not so efficient screw would be, for example, if you have a bolt and you hold it up and it just doesn't unwind. That's terrible. That's good. This kind of screw in a machine means you got to be very careful on a vertical axis, because when you take off the brake, let go of the brake, or stop holding the motor power, the machine will fall. If the machine is powered by a lead screw, it's not so efficient, but if the motor stops, boop, power of the motor goes out, it's not going to move. So there's where friction can be your friend. Remember, reciprocity, the yin and yang. The spreadsheets that are available with the course screwforce.xls, of course, lets you do things like put in the motor torque, speed, diameter of the thrust bearing. Diameter of the thrust bearing? Yes, it turns out that when you're calculating the efficiency of your system and the torque you need, Remember how we showed how the screw shaft was held in bearings? The very fact that the screw shaft is held in a bearing system, there's going to be an efficiency associated with the screw shaft. There's also going to be an efficiency associated with how good these bearings are. And if it's a rolling element bearing, it's probably very high. If you start thinking about the head of a bolt and you are trying to clamp together two surfaces, because the bolt is just a form of a screw, right? And here's the nut. When this nut contacts, let's say you have a washer in here, in the frictional loss between the nut and the screw happens at this small diameter here. The frictional loss between the nut, the washer, and the part happens at a much bigger diameter, typically almost 1.5 to 2 times the diameter. So if you think that the frictional losses in a screw system are high when you have just a regular plain nut and bolt, they're even higher typically between the nut and the washer interface, which is why it's very important when you're using bolts where you want to get a prescribed force to preload elements together, for example, in doing a structural joint, that they be properly cleaned and lubricated as the torque is applied. In this spreadsheet, you'll notice are the elements, the screw thread efficiency for raising and lowering the load. Why should it be different, raising and lowering the load? What's going on there? Why is that happening? Well, remember, a screw is just a wedge. And I'm sure in physics class you remember this problem of if I have a wedge and I have another wedge on top of it, is there some angle alpha such that when I push down with a force here, and given there's a coefficient of friction mu between the wedges, I don't get any motion? That's called a self-locking taper. On the other hand, and that's when this is a very shallow angle. This is typically about 10 degrees. On the other hand, if I have a wedge, very shallow wedge, and I push in here, I know that the shallower the angle it is, the easier it is for me to push this wedge in and move this part up. So instinctually, you should know that, there's a difference between raising and lowering a load. Here, I might be able to push and squirt out the load, the wedge. Here, no matter how hard I push, I ain't squirting out that wedge. And you can run this experiment at home, particularly if you have a sibling with a watermelon seed. It's a really fun thing you can always tell the interesting engineers to be in your neighborhood, because they'll be the kids playing with a watermelon seed and finding there's a point in the watermelon seed where you push and it doesn't squirt out. There's a point where you push and it squirts out. So remember to have some fun with this stuff too. Okay? So very powerful spreadsheets that give you a lot of detail in predicting what happens to the screw. Now, you figured out, I apply the torque to the screw, I get this much force out, the losses, the efficiency, fantastic, great, go for it. You also have to be worried about, you can put so much torque on the screw that it breaks. There is a rule in designing heavy equipment that you never ever use, it depends upon the company, anything less than, for example, an 8mm diameter bolt. Even to hold on a little cover plate. Why do you need such a big bolt to hold on a little cover plate? This is ridiculous. Get rid of those bolts. Cheaper, 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 cheaper. Well, you got to remember that a guy like me comes up to work on the plate. I'm working on my machine. I put my wrench on it and bang! Break off. Bolt wasn't big enough. No wonder it broke. Stupid engineers. So it's not just that you're designing the stress in the bolt for the function of move fast or raise a load. Always remember the function requirement on your machines, human tolerant, because humans can be very, very rough on machines. My students know that If the hardware can survive Alex coming in and playing with it, then it's probably okay. This spreadsheet, part of lead screw design, and you can always combine these things and write your own, of course, goes and calculates, and they're very straightforward, simple calculations. When you apply the torque to the screw shaft, that causes shear stresses in the shaft. It also causes, for example, tensile loading in the shaft, or maybe compression. So anyways, when I come up here and I go, and I'm twisting the shaft, it's stretching it as it goes to compress the part. So I'm applying torsional stresses due to torquing the bolt, and I'm also applying tensile stresses due to the fact that that torque goes through, acts through the lead, and the nut doesn't want to move, so it stretches the bolt. That detailed stress case is handled by the, for example, von Mises stress criteria, and you have to consider both of those effects. You also have to be worried about how much thread you actually engage, because remember, when you're tightening that screw and the nut doesn't want to move, here I'll try not to strip the threads on this screw, that all the threads that are engaged across this nut here want to pull off because I'm putting so much tensile force on it. If you're putting a bolt threaded into a hole, how much threads need to be in the hole? You can run through the analysis of, I want the shear area of the threads times the shear stress of the material to be on the order of the cross-sectional area of the bolt times the tensile stress. And what you will end up with, that the length of the nut that is engaging the shaft is about equal to the diameter of the bolt. That's the minimum. So typically people will seek to engage 1.5 to 2 times the length, the diameter of the bolt as the engagement length of the thread, to give you a good factor of safety. Okay, so back on the functional requirements of this system, we said, okay, we want to move fast. Very fast. Well, we want to be careful. We know that if we go too fast, things can start shaking and rattling. And there's a condition called shaft whip. And what shaft whip is, it's a torsional vibration mode. And what happens is, you can imagine, let's say we have a guitar string. Twang. And I know if I pluck it, it goes, twing, darling. Oh, well, no singing at this point, but you know what I mean. And how's that got to do with anything associated with rotation? Well, everything will have a natural frequency, and nothing is perfect. Almost nothing. And this screw shaft, as I drew here, is not exactly straight. So that tells me that if this is the average center of this is the straight line, the center of mass of that screw shaft will actually, depending where I am along the screw, be somewhere off center. It just will be. Nothing is perfectly perfect. But whereas this line here is the exact center line between these 2 points, the screw center of mass will deviate because the screw can never be perfectly straight. That tells me as I rotate about the ideal center, I now have a rotating mass. So it's it can cause an instability. It's a force that's shaking things, pushing on things sideways. That can excite the natural frequency of the screw shaft. So the rotational speed can excite the bending frequency of the shaft. There's also a torsional vibration mode, but it's in these types of long shafts, it's really the sideways bending mode that's excited by the rotary speed. Now, physics is your friend here also again. What you find is the following curious thing. When the nut is all the way at one end, on this plot here of critical speed versus position of the nut, so when the nut is all the way at one end, the shaft is sticking out a long distance, even though if it's supported at both ends, and the shaft starts spinning at really high speed, so the critical shaft speed is very low because the shaft could start going wobble, wobble, wobble. But every time the shaft turns, the nut moves. So you see I'm faced then with a shaft that is supported by 3 points, multiple points. And because the natural frequency goes like when you work that out, goes like 1 over the length squared. If as the screw turns, here's the support here, and the nut is supported obviously because it's held by the carriage. This length changes very rapidly as the nut moves rapidly. So the longest length unsupported of the screw shaft becomes the dominant length that controls the natural frequency of the system, which is why you see this trace here of the critical shaft speed rises very rapidly as the nut moves to the center of the screw. So here the nut is in the center of the screw. And over here at the end, the nut is on one end of the screw. Your controls people may say, we have to move this machine bed very fast. Whoop, go over here. Average speed, 2 meters a second. What you don't want to do is say, okay, I have to go 2 meters a second. That's equivalent to this speed of the shaft, and I don't have shaft whip, and I know my shaft length is, this full unsupported length when the nut is all the way to the end. You don't want to assume that this is the length that's going to cause the instability at your 2 meters a second, because when you first start out, you're not moving 2 meters a second. By the time you get up to 2 meters a second, the nut has moved here to this position, for example. Now the shaft length that's unsupported is much lower. This is the kind of curve you get. So now you start thinking, if I make the shaft not have shaft whip, assuming that this is the maximum speed I'm going to go at, my limiting speed, you end up with this really big diameter lead screw shaft, which then in turn, remember we talked about earlier, the motor torque gets really high. How did the motor torque go with? The diameter of the shaft to the 4th power. So this is where system design comes in very importantly. See, we've went through the stiffness of the shaft. This motor torque is a function of diameter also, and we worried about the stresses in the shaft. And now we're worried about the shaft dynamically shaking, also affected by the diameter in a big way. But we notice now that, this kind of triangular shape here, this implies that if as long as the motor is going at a speed just below this curve, and the controls people will tell you if I want to go from A to B as fast as possible, for a real physical system, you typically use a triangular velocity profile. Lo and behold, the two relatively are close together. What you don't want to do is let your controls people do this, a true triangular profile, because then you will cross over this critical shaft speed curve 4 times. So you'll start moving and the machine will go, and it'll have these, what was that noise? Is the dog in here? You need to be able to stay below this critical shaft speed. And this is true also for belted systems. When you accelerate belted systems, what's the longest unsupported length? It's constantly changing as the carriage is moving by. This is where machine design gets really, really interesting, that you can design the machine in concert with the control system. So by smart motions, you can reduce the size of machine elements, not only to reduce the cost in the end, but to get much higher performance. Because if you can make your machine with smaller parts, you often have a much more efficient machine and a smaller machine and a cheaper machine. Cheaper as in low cost, but you can still get very high quality. So let's think about the mounting of the screw. We just talked about it earlier for how do you mount the screw shaft to deal with thermal strains? How do you tension the screw shaft? How far apart should your bearings be placed such that the screw shaft, as it goes into the mount, thinks it's built into a wall? Earlier, notice we had that your natural frequency can be much higher if the screw thinks that the end is a fixed support, right? It can be a factor of 10 higher with a fixed support than you would get if it was simply cantilevered support. How do you do that? Well, you need to make sure that your bearings are mounted such that they grab the shaft effectively by several shaft diameters. Remember the topic 3 fundamental principle, St. Benet's principle. If my screw shaft, and these are ball screw support bearings, and we get into the topic on bearings, we'll talk about why these are these instant centers, the lines of action through the bearings, why they're like this, and why they're mounted back to back. So it can take loads either front to back, and now the effective centers are from here to here, and here is the shaft diameter. So we've got 1, 2, 3, roughly 4 shaft diameters effectively holding this screw shaft. This screw shaft now thinks it's welded into a wall in terms of bending. It is perfectly rigid. If we had brought this bearing as a mount like that, which is often how you buy these mounts, you may have about 2 shaft diameters held. That's about halfway. It's not quite exactly rigidly mounted or fixed mount, but on the other hand, it's not simply supported. It's halfway in between. So you will want to make the assessment. Do you, based on is it a high-speed machine, are you happy with simply supported beam and the natural frequency you get, and hence the type of velocity profile you can achieve? Or do you really need that fixed support so you can have your first natural frequency roughly 50% higher, so you can move your machine that much faster, but it requires a more complicated bearing arrangement. Everything is a trade-off. Fortunately, you now are familiar and happy with writing spreadsheets to do these calculations, including cost estimates. The other important thing on mounting of the screws is where do you attach the nut? Notice my assistant up here is pointed to this very important figure that shows you have a trajectory of the motion carriage your screw is moving, and it's never going to be perfectly straight. As beautiful and marvelous and wonderful as you'll have these linear bearing systems now and then, when they move, as the carriage moves back and forth, the bearings aren't perfect and it's wobbling up and down by some millionths of a meter. But it's very, very stiff. Meanwhile, the lead screw attached to the carriage, the shaft is not so stiff. It's mostly stiff this way, but in bending it's not so bad. Or it's not so high. So it'll tend to go along for the ride, but there will be some finite radial stiffness to the screw shaft. Here's the nut. And if the screw shaft, remember we said earlier, is not exactly straight, it can't be, such that the screw shaft has some shape and the bearings have some shape, the two, when you bolt them together, they'll come to some equilibrium position. As you move them back and forth, they'll be pushing on and off of each other. If you're trying to design a really high precision machine, the slightest little rotational rumble of the screw is going to be pushing on the carriage, causing the carriage to bump with every rotation of the screw. And you want to mount the nut in the center of the carriage at the center of stiffness such that the carriage will just go up and down. You don't want the carriage to tilt forward as it moves, which would happen if the nut was mounted off the center of stiffness, because that would cause the whole carriage to tilt. Costs a little more of a pain to get in there to mount it in the middle, unless you do the design right. But if you really, really care about the highest precision, it'll get mounted in the middle. Now, another special thing you can do with screws is differential motion. And for example, this is called a hand screw. A company called Jorgensen has made these for decades. And if I grab both of these handles, and what would happen? What would have to happen to these screw shafts so I could go turn the handles this way? And as I'm holding the handle, and the reason I didn't bring this in is I want you to learn to picture this stuff in your mind. What would have to happen in order as I do this with the handles? So the handles are not rotating, but they're moving around here, the center. The handle doesn't rotate because I'm holding it in my hand. The system revolves. The screw shaft doesn't rotate, it's attached to the handle. That means the relative motion between the screw shaft and the nut that is included in this little bright silver rod, there has to be relative motion, rotational motion between the screw shaft, which is not rotating, and this head, wooden head, which is, because I'm doing that. How do I do that and have these jaws move together parallelly? How do I have a robot gripper such that when I turn one screw, it closes? How do I do that? And I happen to have that robot gripper here. And the interesting thing is, this robot gripper is 30 years old, 30 years young. How is it such that, and the motors are taken off in the end here, if I have a motor for this one, motor from this one, right, that if I turn the screw, that the gripper hands come together? How is that? How can that be? Because if I turn a screw, it goes one way. How do I get that? Let's look at this. What is going on here? On the left hand, I've got a robot gripper hand, and then I've got one on the right hand. How can the left one move to the right and the right one move to the left when I turn one screw? Well, the functional requirement was, for this machine, motor, turn screw, parallel motion of the jaws, such that I can pick up a part always at the center, regardless of the size of the part diameter. Two grippers, such that in a lathe, I could have one part being finished on the lathe. The gripper comes in, wish I had more fingers, and grabs the part, takes it out of the lathe. The robot wrist puts in the unfinished part, goes to take the finished part away and put it down and grab a new part while the lathe turns on right away and starts machining. Hence the desire for the double gripper. Hence the desire for this center line where I grip at to always be located in the same place so the robot regardless of the size of the part, always comes into the same place. So I think everybody's seen now, this screw has a right-hand lead and a left-hand lead. One screw shaft can have two leads ground on it, two different or opposite leads. Guess who designed this 30 years ago? It worked out really well. This idea of differential motion can be used in other interesting ways too. I could have, here's a 4-bar flexure. Remember the flinkages we talked about in topic 4. And if you read in the text, you'll understand and remember why I'm pushing on this flinkage in the middle here, as opposed to pushing up at the top. You want to read the text to see why. It's a very important thing for high precision stages, to minimize your parasitic error motions. Remember that fundamental term. Very important. What is going on here? Is this a left-hand screw and this is a right-hand screw? Not always is differential motion just between left and right hand. Remember earlier we talked about having very high forces from the lead. The other thing you want from the lead of a screw or the transmission ratio is I want to go up and just go woof, turn the handle a full half turn, and I want to have the stage move forward a nanometer, well, micron, very small motion. I want to have a lot of rotation here and have very little motion here, for example, very high precision resolution of stage motion. How do I do that? Well, remember that we said that the linear motion, or the lead, is the distance that I travel forward when I go, how far? In one revolution. Okay? So if I have a screw, here's the nut, there's the screw, and the nut is connected to some very high precision motion stage that I want to move tiny, tiny bit. Let's say I'm moving a part under a microscope. And I want to rotate this screw shaft. And I want to move the smallest motion here. How can I do that? I'm not worried about forces. Well, it turns out that I need to have a really, really small lead. So if I want this to be 1 revolution equals, let's say, 1 micrometer, which is 1/1000th of a millimeter, that means the lead of the screw has to be 1 micron. The lead of a screw with 1 micron, the thread depth would be so small, you couldn't see it and it actually wouldn't work. Bummer. Can't do it. Think about relative motion. If I have 2 nuts on the screw shaft here, and this one has a lead of L1, and this one has a lead of L2, in other words, the thread is like this, and here the thread becomes different. This nut is anchored to the ground. This nut is anchored to my motion table. And as I rotate the screw is going to advance forward here. And if this nut was free to turn, nothing would happen. It would just drive along forward. But if this nut is not free to turn, because this nut is actually anchored on a linear bearing here, what happens? Can you guess? Can I make it such that as I rotate this screw here, the screw is advancing and pushing this nut, but the screw is also turning in this nut, where this nut then goes and unadvances itself. And indeed, you can do that. That's called a differential screw. So instead of having to have a lead of a thousandth of a meter, I could do something like this. I could say the effective lead equals what? What if I had so many threads per millimeter? So I'd have number of, let's do number threads per millimeter, 1 for the first one. And then I have some other different number of threads per millimeter. For the second one. What relationship is here that I can make this work? Well, it turns out it's very simple. And if I want to make this some lead L effective, then what I have here is I have some lead base. And this is lead base plus L effective. Okay. So if I want this to be 1/1000th of a millimeter, I could get that by 2 threads. One of them, which may be, say, something really easy to do, 1 millimeter. And on a high precision machine, I can cut a thread that is 1.001 millimeters. That I can do. I can realize a 1.001 millimeter thread. I can't realize a thread that's fine. So this is an extreme case here, but you can do things like this. This is in the field of instrument design and high precision instrument design. You can also do differential screws to cause all kinds of fascinating motions in devices. This is a chaos device that you can read about in the book or on the web, where you can take pure linear motion in one direction and get output of XY linear motion in the stage that's driven. Wow. Where else did we want to maybe get X and Y motion very simply? Where was that? Maybe we can be using this type of chaos table for XY motion, have a real simple device here to get really nice XY motion just with one actuator system that just moves in one direction. It may not be the best one, it's something to think about. So this is where we have to remember when we're working on things and you're reading about things, you can catalyze different thoughts. And when I'm working on a really tough design problem, I don't just sit down and say, okay, I've been doing this for 1,000 years. I really know a lot. I'm going to solve this. Think. This is why the office is the way it is. This is actually not the office. This is the design playland, right? I've got stuff everywhere. I've got books, internet, and recreationally, just going through stuff, play, even when you don't have to. You do it because it'll trigger thoughts and ideas that you otherwise may miss. Very, very powerful design tool. Differential motion also can be achieved virtually to get very, very, very high pitch or very, very small lead with something called a traction drive screw. Here you have a smooth shaft, and as I turn it, it moves. How is that? Well, this company, Zeromax, makes an actuator. It's called a Rolex actuator. And these are ball bearings, rotary motion ball bearings, mounted at a slight angle to the shaft to make it look like the lead. And as a matter of fact, the angle that these are mounted to can be very, 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 very fine, such that I could make it so I could get a very small pitch effectively. This one actually is set fairly large. This device was designed originally so I could have a lead on a smooth shaft, but it also has a safety feature that you see it can be slid if the screw comes to the end of travel and keeps turning. With a regular screw thread, which is a positive mechanical engagement, something is going to break or stall. So this is a very, very nifty device to have in your design toolkit. Now, we mentioned this term earlier of preload or stretching the screw to deal with thermal strains. So it's not just for dealing with thermal strains in terms of preloading the bearings to stretch it. It also has to do with the fact if you ever put a nut on a screw shaft and it rattles, and as you're trying to get precision motion back and forth, as you're driving forward, if you then stop and go back, you'll end up with backlash or rattle, the rotational motion of the screw shaft that's required before the load will reverse up. And that's not acceptable in many types of machinery. So you get that by reversal. This nut, when I'm going this way, is feeling really good. There's no backlash, but when I reverse direction, you got to pull it back and you have this lost motion. So you use typically 2 nuts mounted back to back. Or if it's a rolling element contact thread, you can use the balls that are loaded in the grooves such that the balls are preloading the grooves and spreading them apart. So very doable, but you have to be aware of how much your backlash you're trying to accommodate and the spring action of the nuts and the shaft to make sure you don't arbitrarily put so much preload on this system that you're lessening the life of it, because you can use up the life of the machine by having too much preload. The opposite of that is flexibility. Maybe you don't want a really high stiffness machine. Maybe you want some softness or flexibility to accommodate misalignment. You can imagine grippers that are made on rubber lead screws, so you can have differential leads very easily. This was a gripper we did long ago that when you turn the screw shaft, you could have a whole bunch of nuts attached to grippers on it. This is actually from a device for picking up devices at one pitch and spreading them out to another pitch. Eggs, computer chips. This lead screw we had built worked really, really nicely. And it was based on using a smooth rubber shaft, or a shaft with a smooth, compliant rubber layer, and then each nut had a different lead. When the nut was engaging the rubber, it deformed the rubber and it made its own screw thread. This is from a CD drive. Here, the lead screw has to be very, very low cost and have absolutely zero backlash. How is that achieved? It's achieved by the nut is actually not a full nut. It's just a part of a thread engaging this lead screw. And that is spring mounted radially, so this trapezoidal thread shape of the nut is driven into the trapezoidal thread shape in the screw, and it's preloaded radially that way. The trapezoid preloaded in the other, under the receiving trapezoid, just like the timing belt teeth we talked about yesterday. So never be too limited in how you think about achieving the functional requirement of preload. Some sort of spring somewhere in the structural loop is stretched somehow and held in order to take out any gaps that you may have, regardless of how the system may move. We're going to end this section here by thinking about how do you use lead screws. This was a machine design contest example of a screw being used to drive a boom to pick up an arm. Just like a crane, where instead of a hydraulic cylinder, you use a lead screw. I want you to think about this in terms of whatever designs you were thinking about now for your table for the drill press. How would you use lead screws? What sort of forces have to be required? What sort of stiffness is needed in the system to resist the drilling loads? So as you're pushing with the drilling loads, it doesn't move away from you. How would you use lead screws in one of these hexapod machines that we've talked about earlier to make the hexapod platform move? How would you do that and control them? Where would the torque be applied? Where are the motors located? This is a very big challenge in the design of hexapods. How do you actually get the struts to expand? Okay? All right. We'll come back with gears in a little bit.